Hello, everyone, and hi, everyone online as well. Some of you can see me. For those who can't, I'm Andy Wickert, an associate professor here at the U in the Department of Earth and Environmental Sciences, as well as right here at the St. Anthony Falls Laboratory. And today we're having a special off-schedule seminar, which we're welcoming Dr. Zach Hilgendorf, assistant professor at University of Wisconsin-Eau Claire, to tell us about his studies of the recent failure from last summer of Rapidan Dam in southern Minnesota. So Dr. Hilgendorf received his bachelor's in environmental geography from UW-Eau Claire itself, so he's gone all the way back around. He then did a master's across on the other side of Mississippi in St. Croix here at Minnesota State Mankato, so about an hour and a half south of us, with a good colleague of ours, Professor Phil Larson. And following that, he went out west to Arizona State University, where his studies then took him from Arizona and across to coastal California to understand landscape restoration, combining ecology, geomorphology, coastal zone science, and quite a lot of kind of classical geography, 21st century geography with photogrammetry, creating digital elevation models, and looking and change detection across ecosystems. He's now taken that skill set back to Eau Claire, where he has, where shortly after his return to the Midwest, we had last summer this major failure of the Rapidan Dam, which in fact made international news. And since then, Dr. Hilgendorf led us in receiving a NSF Rapid grant for that. And we're gonna hear about his work characterizing the changes through a combination of surveying, drone photogrammetry, other data sets since that time. So I'm not gonna take any more time away from him. And with that, welcome again, Dr. Zach Hilgendorf.
Thank you, everyone, and thank you, Andy, for the introduction. Big shout out, just because I saw them on the online chat, to Rick Moore and the Blue Earth County government crew who's watching in, so I'm vested interest in the talk that we're giving today. If you're interested in the RAPID project itself, that's what the little QR code is there for. We can pull that back up once we get towards the end there, but the talk today, I like fun talk titles. So rapid changes at the Rapidan Dam. You can imagine that the word rapid and the RAPID program and Rapidan Dam has been a source of many jokes for me. But rapid changes at the Rapidan Dam, examining the geomorphic impacts of an evulsive dam failure, Blue Earth River, Minnesota. I'd be remiss if I did not mention my wonderful colleagues, Dr. Andy Wickert and Dr. Phil Larson, who are my co-PIs on the project. We're all doing some really fascinating stuff. I'm going to talk a lot about all of that today. And I like to start off with acknowledgements because it's without these people, there'd be nothing to acknowledge. First off, Andy Brown is over down at Minnesota State Mankato. He's a senior geoarchaeologist down there. He's also our drone pilot. So he and I program all the flights, take care of all the fun stuff. A lot of the incredible imagery and videos that you're going to see today were provided by AW Aerial. When the dam was failing, he was a local guy who was doing a lot of drone flights. He's also got a drone contracting business down there. And I asked if he would be willing, could we buy this? And he's like, oh, you're doing it for research, you can just have it all. So he just gave everything pro bono. And I made sure that he knew he'd be shouted out to the heavens every time I got the chance. Blue Earth County Public Works, they've been instrumental in providing us data, some of the stuff that you'll see today, so incredibly crucial, and we're very grateful for them. And the Minnesota Department of Natural Resources, again, a lot of data sharing. We're a collaborative group. And these three hooligans here. In the middle, Ella Gould. These are all two of them. The two on the right are geography students at UW-Eau Claire, undergraduate research collaborators. Nick on the left, he is a biology student we've been trying to pull towards geography a little bit. Ella is going to be going on to her master's to study this at Mankato starting in the spring. So you'll hear plenty more from us as we go forward. So first off, we're going to talk about the project objectives. What were we trying to do with the RAPID project? What has it led to now? And then we'll talk about all the fun sciencey stuff. So the community objectives, right? The RAPID program itself is to look at kind of rapid response to natural or humanitarian disasters. It's basically money to get out and get the data before it perishes. In this case, perishing was not being able to capture things as they were happening in time. So our community objectives here, recreate the progression of the Rapidan Dam failure, just to understand what actually happened and what does this mean as we consider kind of changing climate and dams throughout the rest of the nation and across the world. Quantifying the volume of sediment that was being mobilized from the reservoir, just to kind of understand, okay, how much is coming out? And we'll talk about why this is really important here in just a couple slides. Characterizing the potential impacts on the hydrological and ecological systems. This is kind of more of the work in the future. We're kind of laying the groundwork for it now, but much of the sediment upstream of the dam was a little problematic. From our scientific objectives, the nerdy side of things, right, we're very interested in kind of comparing the failure of the Rapidan Dam as almost an in situ experiment in a natural analog of transverse drainage evolution. So basically, how do rivers carve new paths and create new channels for themselves? This is really akin to something we would call either basin spillover. So it's a really good kind of natural lab to kind of test out those theories that have really only been done in modeled flume studies before. And then contextualizing the failure compared to kind of regional fluvial hill slope relationships. Throughout Minnesota, there's a lot of hill slope failure concerns. Right here on the Mississippi, we have a lot of them as well. So kind of understanding what a failure like this means for the overall sediment budget is kind of on our long-term plans. We're going to focus on the top two today, recreating the progression. So we've got a lot of fun imagery to look at, and then quantifying the volume and kind of looking at what this means for the system as a whole. So kind of getting into the nitty-gritty, if we just kind of contextualize this a little bit more, the why we care of the project, right? There are over 92,000 dams listed in the National Inventory of Dams. With aging infrastructure, right? The average age of dams right now is about 64 years old. 30% of those are significant or high hazard. 9% of those are unsatisfactory or poor conditions, and then 4.5 of those fit both criteria. Rapidan was one of the 4.5 that fit both criteria as being significant or high hazard and unsatisfactory or poor condition. Some of the dams that have seen recent failures are not in that position. They're in this position because of some of the other problems we're experiencing, like changing climates. One of the big concerns with our infrastructure is it might not have been built to the specifications that we are seeing now. As we're seeing changes in precipitation throughout the United States, this is just modeled between 1901 and 2023, right? The darkest blue, or I guess almost a tealish green color here, is 30% increase in precipitation between 1901 and 2023, and just their average annual precipitation. Here we are, that black star is denoting where Rapidan is. We're just a little bit northeast of that. They're generally seeing, as we'll see on another slide here, about 5 to 10% across the entire basin is how much flow we're estimating is increasing with our kind of current climate projections. And it's also known, this is a lot of work done here in the state, stream flow in Minnesota, 20th century agricultural drainage, and then human amplified changes in precipitation runoff. There's a lot of linkages between how we've been hydromodifying our landscapes and the implications that has for things like flashiness within our storm hydrographs, nutrient and sediment entrainment, and what that means from an ecological perspective, and then from a sediment budget perspective, from all the way up here, all the way down through the Gulf. Right, if we kind of look at just some of the many ways that we've kind of been modifying our systems, right, southern Minnesota is very heavily farmed. So as such, we need to basically hydrologically modify our landscapes. Down here particularly, there's some old glacial lake deposits there, some glacial lacustrine stuff that makes it very difficult for water to move through these systems, but also really good for farming. So if we can get the water off the surface better through things like subsurface tiling or through ditching, then we're going to be able to create a better yield and provide more support for our farmers. This is actually a picture I dredged up out of the annals from my master's work, where I was doing some work on a ditch in southern Minnesota. This one right here, as a matter of fact, County Ditch 57 in all of its glory. But we were looking at what were the nutrient and sediment loads and peak discharge coming through this system in response to a series of best management practices that that had been installed onto the ditch. You can see here, right, on kind of this would be kind of the rising limb based off of just how much time it's occupying, right? You can see this nice chocolatey milky color, and that holds true for a while. So you can kind of understand, right, if you're getting water off the surface quick, it's hitting the ditch that much more quickly, but then it's hitting the rivers much more quickly. And if you consider the Rapidan Dam and its position in the central Minnesota landscape, it served as an interesting sink for a lot of these problems. If we look way further back, I said my talk title was Rapid Changes, but our story starts a few thousand years ago. We look at a little bit more recently, 40% of Minnesota lakes and streams are impaired for conventional pollutants. In the Minnesota River alone, it contributes about 85% of the sediment load, 45% of the phosphorus, and 56% of the nitrogen to Lake Pepin, which obviously is a big problem because Lake Pepin's impaired in the upstream for turbidity, for the downstream, usually nutrient impairments. So they see things like algal blooms that happen frequently during the summer. That's not good for your economy. If you are a lake city, you rely on that economy during the summer. And if, well, it's being marred by things like algal blooms, that's not good for your bottom dollar. There's also been a 15% or 15-fold increase in phosphorus to Lake Pepin compared to our pre-settlement rates. That's some work from Engstrom et al. Here, this is from Belmont et al. Right, we can kind of see just that increase here in sedimentation rates estimated from pre-settlement all the way through kind of to the present day. If we look at the Minnesota and LeSueur River watersheds, there's been substantial work done. Our watershed of interest is the Blue Earth. This is wholly known as the Greater Blue Earth River watershed, kind of this area that I'm highlighting here with my laser. About 68% of the Minnesota River ends up being utilized for things like corn and soybean cultivation. Contributes about 5 to 7% of the nitrogen load to the Gulf. The tributaries, this is on the geologic side, are still responding to base level fall. Think of the draining of Glacial Lake Agassiz through its southern outlet, which ends up being the Minnesota River Valley. So they're still responding to that. Karen Grant at Duluth has done tons of work in the LeSueur River Basin, kind of looking at where that Nick zone is progressing. And it plays well into our story. And in this case, our uplands are the greatest source of fine-grained material above the Nick zone. And oftentimes that is coming from these very intensely used and needed farm fields. Here, if we look throughout the Holocene, right, negligible contributions from our upland source, kind of a nice Trimble, Coon Creek style diagram that we see here. But if you look here, 23 below the Nick, 45 up the Nick. So that's in megagrams per year. Now, if we look from a pollution perspective, right, we can see in this case it's grayscale. The darker colors are more polluted watersheds. Our watershed is this kind of moderate gray right through here. We see the LeSueur is much darker. 7 Mile Creek just to the north by St. Peter is a little bit worse. But these are average estimates between 2007 and 2015. These were from the Minnesota Pollution Control Agency. I just mapped them out so we could actually see something here. But if we're looking at yields, right, milligrams per liter, so the water side, and then kilograms per hectare, the yield side. Many of these, particularly if we look down here, so here's our Blue Earth, right? Milligrams per liter, 170 for total suspended solids. Our total phosphorus, milligrams per liter, about 0.3. Nitrates and nitrites, we're in about 7.62. So we're getting some decently high numbers. And you got to consider if terrestrial plants love them, aquatic plants love them too. So we have a lot of other concerns as far as ecosystem health with these types of systems. Now, if we look at Minnesota, actually I'm fairly positive these maps came from Minnesota U of M systems. We're looking at percent change based off of two different emissions projections, RCP 4.5 and 8.5, so kind of our moderate but more and more expected resultant concentration pathways emissions projection for where we're going right now. RCP 8.5 is kind of what used to be called business as usual, right? So if we were to keep polluting and emitting the same way, this is what we would expect. Any way you slice it, there's about a 5 to 10% increase in precip throughout Minnesota by the end of the century. And about a day or so, more intense precipitation. So these are high magnitude events like the one that we saw striking the Blue Earth River just last year. These changes and the changes that we're seeing have been pretty evident in recent years, particularly 2024. If we go way back to a much more tumultuous time, COVID, right at kind of early stages of COVID, the Edenville and Sanford dams in Michigan failed. This was a kind of a daisy-chained catastrophic failure where one failed, that water inundated the next, and that downstream system failed as well. June 24th of last year, the Rapidan Dam failed. A few weeks later, the Manawa Dam in Wisconsin, central Wisconsin, failed. This dam was not poorly rated. It was actually rated in good condition, but a high magnitude storm struck the watershed and caused this one to fail, and they had to evacuate a good chunk of the town. And then the same thing down in, this is not Nashville, Tennessee, this is Nashville, Illinois. So the Nashville Dam failed just a couple of weeks after that. All the same type of high magnitude event that has been starting to overwhelm these types of watersheds. We're going to obviously today focus on the Rapidan. So if we look just kind of a historical perspective, the Rapidan was constructed between 1908 and 1910. It's about 26.5 meters tall. It was about 145 meters long. And up until about 2020, when some of the intense storms that we had hit the Minnesota River Basin, it was generating hydroelectric power. It was no longer doing so, even right up to its failure. It drained about 6,300 square kilometers of the Blue Earth River. Nice, cool picture, kind of just looking downstream from about 1909 of the dam's construction, just some really cool historic imagery from the Blue Earth County Historical Society. This is what it looked like in September of 2009. Back up just a second, that's a 26.5 meter tall dam from bed to top, and that is sediment right almost up to the tippy top. There's a fascinating history of sedimentation that we don't have time to get into today, but you can see, right, there's not much storage capacity left in the dam. And this was pretty evident in a series of reports, one from the U.S. Army Corps back in 2009, and another from Barr Engineering in 2021, warned that, well, a failure of the dam would be catastrophic, would free up an extensive amount of agriculturally contaminated sediments from within the reservoir. The dam was structurally sound, but there were issues with flood release, so letting water run out more quickly, which ends up being a problem for our story. I kind of argue the system was primed for a catastrophic failure. And it happened. 240 millimeters of rain between the 15th of June and the 24th of June. And actually, it's a little bit finer than that, pretty quick over the couple of days preceding the failure. We can see the storm hydrograph from the event. It's the second largest peak on record, 985 cubic meters per second. And early in the morning, right about there, where I have the arrow pointing, water avulsed around the dam. So we're terming this an avulsive dam failure. It wasn't a conventional dam failure like you might think of, the dam burst, water spilled out. The dam was structurally sound. It was still standing and still is today, but water was rising so fast that it overwhelmed the small amount that could leak out from the dam, and it ends up eating around the western abutment of the dam. Kind of an interesting thing here, this is more just from the nerdy science side, the hydrograph gets really goofy right when the dam fails because it's mostly pressure transducer based measurements, I think there. And right as the dam fails, you see a huge spike down before the hydrograph bounces back up. That's what this almost overlapping bold colored line is there. So something that we're kind of looking into and very curious about what that means for the hydrograph. But we can see here, we're looking at our accumulating precipitation normal is the blue line versus what we actually saw over the period of record. So generally speaking, especially right around the time of our failure, we've been well above normal for precipitation throughout the area. About 20 different events that we've monitored and over the time that we've been collecting data. There's a few more over here, but I just didn't have time to work that out. We're actually out in the field collecting data yesterday, so we'll have some cool pictures from that to show you. So the next section that I want to move into, this is one that kind of very near and dear to my heart. I call Changing Landscapes, the Camera and the Geomorphologist. Mark Fonstad, who is out in Oregon, a geomorphologist by training, but somebody who is very progressive with how he uses sensors to investigate geomorphic questions, wrote this really awesome paper called The Camera and the Geomorphologist back in 2020. And it's something that I've kind of taken near and dear to my heart because most of my work as a geomorphologist comes from looking at it through a lens, whether that's the lens of a camera, the lens of my phone, a high-powered multispectral sensor, or some type of active sensor that's emitting a pulse and bringing a laser back. But anything I do is kind of looking at this through the lens of a geomorphologist, to be punny. But if we look here, this is the first lens that we're going to look at. This is a high brow lens, looking at it through Planet Scope, which is a 3-meter resolution. So every pixel here is 3 meters. This is the dam or the system 10 days before the dam failed. So whenever I show these pictures, you'll notice up here I have either a negative or a plus, so days prior to, days following. This is from the 14th of June. We can see the dam fully intact right there. Some things that'll be of interesting note here very shortly is this nice little filled in reservoir area here. This kind of spill through channel that we see in high flow here. Sometimes that's dry. In this case, it's inundated. This becomes very important as we kind of progress through our story here. So let's advance a couple more days. Here we are 1 day before the failure. You can see water is way up. The bridge is getting pretty close, cascading through. We don't see it yet, but water's going to eventually crest right through over here, and it's going to start to spill. I don't have imagery yet. Hopefully I can find some at some point of water actually doing that, but it starts to spill over. It takes out this Xcel Energy power station, takes out a county shed that's just off to the right here, and then it really starts to wreak havoc as a nick starts to develop and eat its way upstream. June 24th, 0 hour here. We see the river avulsing. They're just starting to avulse around the west edge of the dam here. So there we are. This is just a high resolution image from a couple years before. This is the best one I could find. There is a drone image, composite drone image from the 5 days post failure. So we can see, used to be connected all the way through, kind of where I have the laser here, before it rises and starts to cut its way around. Now, back to the day of, we can see, first off, the observant geomorphologist, we can see a bunch of these stair steps here, right? Well, those stair steps are various nick points that are being worked through with varying levels of rapidity. The first one is just some alluvium. We're very lucky that Bar Engineering has done some boring out there, so we actually have that data. This is preliminary, but kind of helps us look at this, which is, back up just a second. Back forward just a second, apologies. There you go. This is basically the surface we're looking at right here, just a little bit more recently. So as mapped by Bar and another firm that was doing boring out there, the top package is alluvium, underlain by till and some outwash, Prairie du Chien dolostone underneath that, and Jordan Formation sandstone, which is what the dam was generally built into. Here is 1 day after the failure. We can see, among other things, those nicks that have been working upstream have been working through that Prairie du Chien dolostone, still hung up on that up here. This is a really crucial moment for the evolution of this story, because once this lets go, it rips upstream in a matter of hours, working through unconsolidated reservoir sediment. We've got some not in situ photos from that, but we've got some great satellite imagery to kind of help illustrate this story. This house ends up falling in later that day. Very fortunately, the family was not in it. They were able to escape, get out. They operated a cafe that was just back through here. Together with the community, they stripped the cafe bare, and we're actually able to reopen it in Mankato. So if you're ever down there, the Dam Cafe is the one that used to be located here, kind of a community staple. Here we are on that 2 days. Now, if we look at the satellite imagery, some interesting things start to pop up. We actually see standing waves, suggesting very high velocity flow ripping through this system, but we don't see them over here during the failure. Over here, those standing waves start to terminate, and you kind of can't really see them in the 3-meter imagery. But if you have access to things like SkySat, somebody was pointing a very high-resolution satellite at the location at the dam during the failure. Notice here, instead of days after failure, I have timestamps, because we're actually able to look at here a nick zone, nick point. You can see those kind of cavernous features moving their way upstream. Here we see it barely an hour later, a little less than an hour later, and it's moved much further upstream. In this case, in less than an hour, it's migrated 80 meters further upstream. Now, as I mentioned, some DNR folks that we had on the ground, this was happening in a matter of hours. That nick had migrated completely up. Now, this is an interesting part because it starts to move its way up this channel, but it's probably bifurcating as well and starting to move up this channel as well. What that means is that there's kind of an interesting wrestling for what the dominant channel ends up becoming, and water doesn't like to flow at right angles. So the next picture should be fun. So here's that vegetated island again. So as we saw in that satellite image, we had the nick migrating up this channel here. So being the shortest length of channel, it's going to get up to and kind of capture the main river faster. Water is still diverting through this lower channel as well, which was the dominant channel prior. But what ends up happening is water starts just hammering this vegetated island here. And this is the only image we have. It's an INSAR image, so it's able to see through. There was a lot of cloud cover at that time. We're able to completely see through it and actually watch this island getting basically destroyed within a matter of hours. This is what it looked like 9 days out after. This is our first full drone flight of the region here. And you can see all these dissecting channels and one small little knob of remained relic level. So this is about 5.5 meters tall. You can see it over there. It looks like, it's basically, it's that last little lip there, the tip of this little island that you see is all that was preserved, which is really useful because it helped us be able to kind of consider just how much was removed. When I was originally looking at this, it's very hard to get out here. We were able to get access later. But you look at this, you're like, oh, there's a little knob out there. And then you get out there and it's 5.5 meters tall. And that's all reservoir infill for when the level had graded and the reservoir had been filled. This picture in the background, that is from this past June. This is from last November. But really cool to kind of get out there and just see that and put it in perspective. We'll come back to this a little bit later. So this video was flown on June 24th. This is 1 year after the failure. There it goes. Just to kind of give a bit of a better perspective on what that looks like. It's a little choppy, apologies, but before the vegetation had started to grow back in, this kind of looked like a Martian surface. It was completely stripped. These logs had been left up there. See these big log snags here. The lower parts of the channel are all very, very large boulder lag as all the fine grained sediment had been stripped out. Hopefully the next videos are a bit better. That one was a little choppy, apologies. So here we are 4 days after the failure. You can see that nick there is a nick, it's right here, but it's almost completely flattened out, much closer to the level of what it is right now. So here, right, July 3rd, you can see this has been completely obliterated and the river itself is slumped back into that southern bend. And here's just a nice video from 9 days post, right? Some really interesting stuff here to show, and we'll look at this a little bit more once we get to more of the data-driven side. Is there the main expansion of the channel of this scarp was through kind of eddy recirculating flow. At least right here, this is the area that the river moved the most to the west, about 120 meters or so by the time it was all done. And you can see this eddy flow kind of recirculating, undercutting the bank, and then chunks of this are just falling off. Here we are 43 days after. In low flow, this is a pretty rough image, but the river actually starts to take on a braided planform. So rather than a single sinuous meandering channel, it's so choked with sediment downstream that it actually takes on a braided channel formation. Here it is this past March, 252 days post-failure. Right, we can see some mid-channel bars, some point bars down here. This is a great one for showing there are 3 active nicks right now within the region. There's a boulder lag nick right here, Jordan sandstone nick right here, and I think this one might be constrained, but there's another one right here that I think was from when they were demolishing the bridge. Here we are, 1 day or 1 year exactly, June 24th of this past year. we had some storms come through, so water was up, that mid-channel bar was inundated. This is we're calling a shadow bar, low pressure zone when floodwaters were really ripping through. That was depositing sediment behind this nice sandstone, Jordan sandstone outcrop. And this one helps put it into context. So this is almost the same. This was complete, I think serendipity would be the term. We didn't mean to do this, and we actually found this image here in the historic imagery, thanks to our wonderful colleagues at Blue Earth County. We're able to kind of, you look at the yellow box, you look at the blue box, you can kind of line up things in the landscape. So this was just as the dam was starting to get undergo construction. So this is the Blue Earth, right as it was kind of coming out of its initial, free-flowing state. And here it is a year ago, or a year after the failure returned to its pre-disturbance state. It's kind of I think a very interesting look at how the system is responding to the failure itself. And here it was yesterday. We were actually out here collecting data yesterday. I did not plan that, but I love that it was exactly 500 days after. I think that makes for a really great talk title in the future. But you can see here is water's just kind of trickling over that sandstone ridge there. We'll look at that in just a second, but those bars are emergent once more. So one of the things we're going to be starting to do is actually look at just how fast these bed forms are moving. We're only able to really do it in kind of their low flow emergent status, but it's kind of helps us kind of track from a volumetric perspective how this is changing and how the sediment is dumping out of the system. And this is just a drone image or drone video looking at water coming through. So this is a really fascinating surface because there's actually a lot of what I would almost call fluting or sculpting features through here, where you either have either an iron or manganese or a magnesium head, and then this kind of shadow form behind it that was getting protected from the abrasive forces of all the sand and gravel moving over it. It's cut through in a couple of different areas, and it's actually undercutting that ridge now. So there's actually space underneath this lip that you see here. This was last November, the 15th of November last year. The red line is basically that line that you're looking at here. And in comparison, it's marched about 2.5 meters on average back in less than a year. I think from some of the March imagery, I could probably go back and pull off what that line looks like. And I suspect it's moved back kind of from some of our summer floods. Which has implications for just how quickly the system is going to respond when this is eroded through and the river is able to adjust back down to that level. All right, so let's look at some of the actual methods side. The camera and the geomorphologist is a fun exercise, but we actually do other science out there too. One of the main things, and really our main tool, is photogrammetry. So we go out and we fly this drone in particular right now. We're actually trying to purchase another one, fixed wing, but this is a DJI Matrice. So we are flying this one, pre-programmed, automated, and very constrained intervals. So basically, there's a 70% overlap between each photo in succession, and there's a 70% overlap between each line of photos. So that lets us have a very high degree. We're seeing one object from roughly 15 to 20 different angles. And because we know how high the drone is flying and we have ground control points distributed throughout the watershed, we're able to, with a very high degree of accuracy, reconstruct what the surface looks like. And from a volumetric perspective, that serves as the impetus to compare time and time and time again. So we also were very fortunate. The USGS was reflying the entire state of Minnesota's LiDAR again. As a Wisconsinite, I'm incredibly jealous of your guys' geospatial data. In southern Minnesota, that flight was postponed. It was supposed to be in the fall of 2023, and it was postponed to April 5th of 2024, which, if we think when the dam failed, June 24th, it was very fortuitous timing because really nothing changed in the river after that LiDAR was flown. So we have a perfect base level to check how much sediment's been eroded post-failure. We have a Mavic 3. This is what a construction company that the county had contracted was using to collect their structure for motion data. This little guy down here. And what we're producing generally is about 2.7 centimeter per pixel orthomosaics. So just imagery and about 5 centimeter point spacing in a high density point cloud. We densify that, or we coarsen that to about 10 centimeters when we get it to the actual elevation model side of things, just because it's within our margin of error. From there, we export the dense cloud, we clean it up, we make surface models about 10 centimeters per pixel, we hydrocondition the surface models, and then we put it into the geomorphic change detection toolset, which was developed by Joe Wheaton and colleagues at Utah State University. North Arrow Research now, I think, runs the upkeep for the package. Free download. It basically takes co-located rasters, and you can use some uncertainty estimates as well, so it can provide statistically relevant estimates for what your bulk error volume is versus how much change you see. So if we look here, right, here's time 1, here's time 2, the dashed line is time 1, the solid line is time 2, and you just see, okay, well, this much deposition happened, this much erosion happened. And blue is, in this case, in all the maps we'll see from here on out, blue means deposition, red means erosion. We also did some stuff using the digital shoreline analysis system, which is a USGS toolkit that is designed for coastal systems. But if you just hold it the same way you would a coastal system, you can repurpose it for riverbanks. So that was just a nice repurpose thing there. So don't worry about this one. This is just showing just the sheer amount of stuff we've done out there. We've been out there and flown drones 10 times. The county commissioned 3 flights. We have 3 LiDAR data sets. So we have 16 different steps in time to investigate how the system's changed since at the earliest 2005 to yesterday, which I think is pretty awesome. If we want to look, this is just kind of the extent of our orthomosaics. So this is the first time we were out there. These other 3 were the flights the county commissioned. And you can see we expanded it once we achieved our NSF Rapid. There's our most recent one. It's a little hard to see, but there are plenty of emergent bed forms that you see kind of poking through. Some nice welded bars and mid-channel bars as well, but it's already kind of in the low flow state where it's back to a braided system. Now here's where our results come into play. So this is what you generally get from the geomorphic change detection toolkit. Apologies for the color here. It should be still decently visible. This is from 2005 to 2012. This is from 2012 to 2024. These are all LiDAR derived models. This one's both of them are a little impacted by the level of the water. That's just not something we can overcome. But what we really want to see here is really the only change was either we see some blue here, that's toe slope development from hill slope failure, or in this case, some bigger hill slope failures that had occurred in the 12 years past from 2024. And this is the fun one. So here, holding all things constant and assuming that no change happened from April 5th to June 24th, we can basically assume that this is the change in the 5 days post-failure. About 217,000, a little over that, cubic meters of sediment were ripped out of the avulsion channel that we see right through here, which I like to liken to swimming pools because that might be a bit more tangible thought. Think of Michael Phelps swimming through 87 of those. 87 Olympic swimming pools worth of sediment were torn out of this region right through here. A maximum depth at this time, just because we were, again, kind of constrained by the water level, of a little shy of 17 meters, an average depth of about 10.5. We step forward in time. Here are the couple of days, June 29th and July 1st, and July 1st to July 3rd. Most of the change post-failure is localized along the hill slopes immediately next to the dam itself. So here we've got that recirculating flow, undercutting and weakening the banks, and that's where we're seeing the majority of erosion post-failure, at least in the week after failure. From July 3rd to the 10th, and then the 10th to August 6th, again, we see that same thing happening. We haven't really got much rain. The faucet kind of shut off after that big storm, so we're actually mostly seeing drawdown from here on out. In the longer intervals, right here, we've got almost a month. You see a lot more change evident than just if you were to look at it from the week or the couple of days. The 6th of August to the 23rd of September, here, because flow is low enough, we actually start to see toe slope building occurring. The system is trying to respond, and I say that kind of anthropomorphizing it a little bit, but it's adjusting to those oversteepened banks. And as it starts to adjust, that slope will become lower and lower and lower until the river is able to migrate and meander back and forth, in which case it'll just keep doing that until it's established its floodplain. We are not there yet. So while in the quiet months, we are seeing a fair bit of toe slope building and hill slope erosion, once you start to turn the faucet back on and our spring rains start to come, that sediment load starts to get wiped out. There is some armoring of kind of a boulder lag right at the toe slope in some cases, but when water is inundating that region, that boulder lag doesn't really do too much. So you can see again, throughout the spring, mostly just building. And then we start to scour that out again. We're removing that toe slope material because we've got, again, here, increased flows. Here we are back in June of this year, June 24th. All of that material has been removed. We're starting to eat back into the bank again. And then this was up to our most recent one. Again, we were out there yesterday, but I haven't been able to work all that data up yet. So this was the state from June to August of this year. Lots of erosion happening at the oversteepened cusp of the scarp, and a lot happening on the face of the scarp, particularly, again, located along the dam. So as water is kind of coming through the dam here, we're kind of constricting it. It's hitting this bedrock ridge. It's kind of shooting through, and I think causing a lot of that recirculating flow that we've been observing. And Ella, my undergraduate student, likes to laugh at this one because it looks so boring, but it tells such an interesting story. Because if you look here, this is our normalized volumetric change. So this is cubic meters averaged by the total extent of the area of observation by week. So basically, how fast are things changing? In the first 5 days, right, we're looking at somewhere north of 14 meters per week, just to put it in that perspective. Obviously, it wasn't going to do that for long until it hits threshold, because we see in that next interval, kind of at the end of June into early July, it's already sitting somewhere around, maybe 3 meters per week, 1.5 meters per week, and then almost nothing for the rest of the time out there. So if we're thinking of how geomorphic systems are perturbed and that rapid response to that perturbation, most of it is kind of excised within the first few days. And then once the system has adjusted, at least in some way, change happens very slowly if it's happening at all. If you compare that to discharge, here we're just mapping out discharge in cubic meters versus our normalized volumetric change, right? As you would kind of expect. In this case, the more discharge, the more geomorphic work that you're able to do in this case. And if you were to look, this isn't up to the most recent in August because a lot more of the channel was inundated. So this goes back to March, which was our last of our kind of low flow status collections that we did. So March of this past year. We could look at about 107 Olympic swimming pools, or about 260, almost 267 cubic meters of erosion within the avulsion channel. The really cool thing here is if you look anywhere from the avulsion channel upstream, erosion is the dominant mode, at least so far. Anywhere downstream, just rampant aggradation. There were 15 to 20 meter pools within the river that the DNR was always aware of, had surveyed, knew about when they were doing fish monitoring, that were 1 to 3 meters, or 1 to 3 feet, 1 to 3 feet deep when the sediment had filled everything in. And this is all the way to the mouth of the Minnesota. Another big problem here is from a fish perspective is now, while fish presumably have passage back up above the dam, the coarse sediment and gravel that's here, they showed us some pictures back in March where fish that had been living in these kind of very shallow, sandy, gravelly pools were just completely rubbed raw on their bellies because they're not sitting in that nice, soft bed that they're used to. Within this shadow bar region, we actually saw about 20 Olympic swimming pools of deposition happen right throughout here, kind of filling in this low pressure downflow zone with a pretty substantial amount of sediment. There it goes. This one's even tougher with the lighting here, but in this case, we're just kind of looking at cross sections from the edge of the lawn that you were looking at here. This is from A to B. So B is the deck of the dam. through time. So the yellowy colors are pre-failure to early stage, transitioning to the blues, and then ultimately to black. It was the later, more developed stage. So you can really see the darker colors you see are less steep with a bigger toe slope package. So it's really cool to see kind of that hill slope failure process in action. If we look at the digital shoreline analysis system, here we see a really good transition from the previous channel, which was outlined by this dashed line here, and the extended state of the avulsion channel here. For the first little interval, about 115 meters within just a couple of days, it avulsed to the west, and then added another, on average, 18 meters or so after that, mostly localized right here. This is, again, right next to the dam. This is where the most change is still being observed. And then that devegetated island, or what we call kind of our denuded veg island, in the upstream reservoir area, about 609 or 1.5 million cubic meters of sediment were eroded through here. There's that little knob that I showed you. It looks like there's color there. That's just because the pyramids and how the pyramids build kind of obscures what that is. If you zoom in on it, there's really no pixels of significant change there. So what are the takeaways from just this part of the project? Well, the greatest change was happening within the first couple of weeks, kind of confirming what in the transverse drainage literature we know is most of that rapid change is happening right at the onset and then relaxing as the system relaxes. That eddy recirculating flow is leading to a lot of localized erosion, expanding the channel and widening it, which is a very natural process. There's just a lot of infrastructure in the way. The river is now hung up on bedrock, but that erosion is progressing. This was from last year. Actually, no, this was from earlier this year, I think back in June. And it's actually extended out decently far here. So a lot of those late summer flows, I think, did a number on the system here. Upstream of it, there's a lot of really interesting problems here. You'll notice some slumping, a lot of slumping happening here. This is all reservoir sediment. That's just going to keep getting mined out as the river meanders back and forth in the upstream stretches. Right now, it's still, generally speaking, a single-threaded channel, very straight for the most part, but with inundation of sediment coming from upstream, this is, in some reaches, kind of taking on more of a braided channel plan form. But then the next, and kind of towards the end here, what's next? Andy's part of this story. First off, I call this one BioBlitzing. So Nick, our biologist over here, we organized what we call a BioBlitz. Has anyone used the app iNaturalist before? Yeah, really awesome app. You can actually organize biological blitzes. Basically, you go out with a group of people and map as many different types of vegetation as you possibly can. And that's what we did with this group of students here, graduate students and undergraduates from Mankato and UW-Eau Claire. All of these dots are points that they mapped different types of vegetation. So Nick is currently working that up so we can understand the ecological succession of this denuded veg island. Mostly it's very herbaceous, stemmy plants that are taking over right now. These are all following kind of low-laying clay-rich layers. You see a lot of expansive clays that were contracting in the dry periods, leaving real runnels throughout the landscape. But when they were also collecting the most water, so plants very preferentially moved right in there. We are trying to map in the channel migration, so just a nice false color infrared of here's the Lesueur, here's the Blue Earth, here's the Rapidan Dam area. So we're actually mapping from down here at the confluence with Wantawan River all the way upstream to the Minnesota River, how the channel has been adjusting in its width and position following the failure. Most of that change is going to be localized right through here and in some of the upland reaches, but it still bears quantification. This is a really fun one. This is a contour map with a bunch of spot-checked elevation from 1911. So this is prior to the filling of the reservoir. So the dam is right here. This is the outline of the river in this nice dashed perspective here. And then there are 10-foot contour lines throughout this entire area all the way down to the Wantawan River, which is over this way. And this is part of the Blue Earth that goes up here. So we're actually going to recreate a three-dimensional model based off of this imagery and try to compare it to our LiDAR to understand how much the reservoir had infilled up to April before the failure, and then how much of that was actually excavated out. And then with Dr. Andy Wickert, some large-scale particle imaging velocimetry. So we're taking videos every time we go out there to try and extract flow velocities off of the imagery. So that's some forthcoming work that we're pretty excited to kind of get off the ground. And with that, I think right on time, I will happily take any questions.
Interesting work. What an amazing failure. So the dam itself, it looked like it performed the way it was supposed to. It looked like the spillway, the top of the spillway got choked by debris, and that it ended up, they were conduits, rectangular conduits, due to the fact it had a roof, which was the road. So, I mean, if the spillway, if simply that deck had been removed and the debris could have gone, and there was nothing to turn the spillway from being a free surface to a conduit, would it have still failed?
So I don't want to speak out of turn here, especially with Blue Earth County hanging out. I want to make sure I'm doing them justice. There was a lot of really interesting historical issues with the dam. In the early 2000s, I think they had to pump an immense amount of concrete into the base because underneath the dam was the bedrock was getting mined out. So they had to basically fix a bunch of those problems there. Some of the sluice gates were unable to be opened because they'd been cemented, or basically the sediment had built up so much behind the dam that there was kind of issues opening those a little bit more. They were impounded by large woody debris. So it was kind of a cascading series of issues that ended up, I think, ultimately leading to the dam avulsing. I can't imagine if it would have hit, if that low point hadn't have been there, and kind of the western side of the channel, I imagine if it had gotten to a point where peak discharge was just going to overwhelm the dam, it just would have flowed over top of it. I think just the makeup of the bedrock out here, having that kind of alluvium underlaid by the till, underlaid by some, the Prairie du Chien, Dolostone was ended up, that was the kind of the real big hang up for a while, and those at least the first 3 days post. I think it was just kind of the perfect storm of being able to quickly mine that out. So if it had just kept cascading over the dam, I don't think it would have been the same type of problem. I don't know, hopefully, I don't know if that answers.
Well, I think it's still unclear.
Yeah, it's
what would have happened.
What could have
if the
happened.
spillway were just unimpeded by these choking things.
Yeah.
I don't, just one other question quickly, and just more of a logistical one. With the gridded drone data, what do you know off the top of your head so you end up with topography, you get, so horizontally, it's not that hard to get decent accuracy, but I'm always curious about if you use photogrammetry in that sense, multiple images getting the same point from different points of view. This is drone stuff. What's the accuracy of the elevations on your grid ones?
Yeah, we try to be relatively conservative with our estimates just because, volumetrics are something that people are very interested in. And I've worked in a lot of restoration focused projects where they have very particular numbers they have to report. So our combination of vertical uncertainty comes from the instrumentation itself, what the kind of reported specifications for that are, kind of the industry standard accepted uncertainty values there. The uncertainty from the reconstruction from this structure for motion. So it reports, I use Agisoft Metashape as the photogrammetry program I use, and it exports kind of an XYZ uncertainty. So we build that in, and then we also build in everything that we use is kind of clamped down to the LiDAR. So if there are kind of minor shifts in the resolution of the ground control points, we lock everything down to the LiDAR. So that also gets an uncertainty value. So we end up on a good day.
Just the drone images alone?
Yep, just all of that.
Aside.
Yep, all that aside. We usually get 5 to 10 centimeters of vertical uncertainty.
Okay.
Yep.
And you have a bunch of benchmarks to help with this, right?
Yep.
Okay. Great, thanks.
Yeah.
Great talk.
Thank you.
Very nice, yeah. I have a question. I mean, after the failure, so wouldn't that make sense just to blow up the dam at that point?
Well, so that is in the works right now. So Bar Engineering, I think, was awarded the bid to deconstruct the dam. I think they were trying to, one, figure out how it was going to be covered from a financial standpoint, but also they were kind of reeling from the failure. So in, I think 2027, last I heard, is when demolition is supposed to start. There was a bigger concern on the upstream side, and that was the County Highway 9 bridge. So there'd been a bridge up there that they were already concerned about in the couple days following the failure, that there ended up being valid concern for, where I think the bridge abutments were actually, they were cemented 40 feet down into reservoir sediment. They were kind of resting on top of the bedrock, as I understand it. So when all of that reservoir sediment was stripped, the bridge became unstable. So that was the first priority, was to get the bid to demolish the bridge. And then the second priority was the bid to demolish the dam.
But I was thinking from the perspective of limiting the damage of the avulsion.
Oh, I see.
I mean, if any kind of perforation would be created in the dam, that would have provided a pathway for the sediment upstream to kind of compensate all the erosion that was coming on the side. And because, I mean, this was, I mean, based on what the story here, it is a particularly bad failure because all the sediment upstream remained kind of intact. And so the river eroded a lot on lateral and eroded all the way without the supply of sediment that should have been used, like in principle. So I wonder if in a situation like this, it would be possible to have a very, very rapid response of, okay, blowing a hole through the dam and let at least the part of the sediment to go down so that there will be more balance between the flow and the sediment.
Basically notching the dam out in time so that it kind of,
At that point, you would limit all the lateral erosion into, I don't know if that's, I mean, it's a kind of Star Wars image, but it would make sense to me that that would be the only way to limit the lateral erosion, to create a pathway and abundance of sediment deposits. So it would limit also the erosion on the mass that this is
I mean, we're still piecing together the story, and you know, we've talked with the county a bit. It was just the whole time it was more of just kind of reeling from this is happening rather than, you know, and they were trying to, because it wasn't the entire Minnesota, from basically Mankato to the cities had gotten just hammered with high flows. So they were kind of stretched very thin on their response. And I don't think anyone expected this to happen. There was threats up until the day or two, I think, before is when it really got real. So I don't think, not wanting to speak out of turn, there was enough of time to respond in that way. That could have been a constructive way to address the problem. But one of the other, at least this is just from talking with the DNR and talking with some other people who kind of dealt with dam construction in the area, they're saying some of these old dams are just tougher than all get up to actually destroy the concrete. So they were saying, you know, sometimes they'll schedule a demo and the demo will be 100% longer because the concrete's just so hard to work through, that could complicate matters in this case. And these ones, this is, I think, around that era, that early 1900s construction.
Thank you so much. That was a very interesting talk for me. My question is rather general because now that you talked about this sedimentation, I realized that this sedimentation problem must be a very common problem, especially with the older dams that have been water coming and going through it. So I'm curious, what's the general procedure that they do to remove these sediments? Do they divert the water and just scoop up the sediments, or they do something else, and what they could have done to prevent this catastrophe?
Yeah, so a lot of times it's kind of general use case. So what is the particular project call for? If you look at, for example, the Elwha River Dam removal, a very high-profile dam removal out west, at the time the largest in the world, it was a very staged decrease. So they were deconstructing and very gradually lowering sediment, lowering the level of the dam so that sediment would, you know, slowly move out. It did lead to a lot of inundation downstream and kind of choked out some of the benthic organisms and the fish there, but it responded much more quickly. Here and there, I mean, it's also much steeper through there, so it's I think easier to mobilize that sediment in a way that's effective. Other places, I can't remember exactly how they did it on the Kinnickinnick River, just across the Cheddar Curtain over in Wisconsin. But there, I think it was more of a rapid drawdown of sediment. So it really is just kind of a project specific. Here, it's interesting to kind of consider. I mean, there's still a lot of sediment that is fully intact that has kind of floodplain forest development on it, which I think is a completely great way to kind of retain that sediment. I think if there had been the option, I know it had been discussed, and there was a lot of talk about what would you do with the sediment that was there, and I think if there had been a way to do maybe a very slow, gradual drawdown and let through a number of years that vegetation kind of recolonize and hold that sediment in place, I think that provides at least a bigger buffer to kind of work and address how it's going to be used. The Blue Earth, in this case, doesn't have a ton of water moving. It gets some peaky flows through it, especially with all the hydrologic modifications upstream. But generally speaking, in this case, it's not going to be mobilizing that sediment that rapidly if it has time to adjust. But the problem with that is money and time. You've got to commit decades rather than what most people have is a few years to kind of address a problem like this. So,
Thank you.
yeah.
You briefly mentioned slope just now, and I was wondering, do you have data on how the slope of the river has changed through this reach?
Yeah. More preliminary right now, just because it's just one of those things okay, once I have a minute to breathe, I'll hammer out the channel profiles. But we are going to be able to extract the channel profiles off of it.
LiDAR? Or...
SFM, so drone based. But we were very, very lucky. The county had commissioned a LiDAR flight on a year ago today, November 7th of last year. 95 West aerial mapping out of, I think, Bismarck, did a big flight here. So we actually have a LiDAR version of that as well. And we are comparing that against the 2024 USGS LiDAR to really look at kind of not basin wide, we don't have that coverage, but much further upstream and downstream than we were able to fly with our drone. So we're going to be able to get channel profiles out of there. It's pretty steep from that lowest nick, the boulder lag nick, probably 1 meter, 2 meters of elevation change from below to above. Another, here you can see just how much there is there. That's a good 3-ish meters, 4 meters there. And there's another smaller one just upstream there that's maybe a 0.5 meter or so. So there's from the lowest point downstream to where, this is here, there's a good 6-7 meters, I would almost guess, maybe 6 meters of height that the river still has to adjust down to. So, yeah.
Has anybody figured out where the sediment went?
We're working on it. It's, I think one of the things we expected to see was large algal problems in Pepin later that summer, and I just don't think we saw them. We put in for an LCCMR to try and do just that, some fingerprinting work with the USGS and some other, U of M and Christy Dolph here and a bunch of others, and that was not. Unfortunately weren't funded for that one, but we're trying to at least use satellite imagery to see if we can track at least sedimentation within the riparian corridor. So that's the next thing that we're going to be trying to do.
I have one more quick one.
Yeah.
Do you fly any multispectral cameras, or are you just...
Not here, not yet. No, I'm trying to buy those drones. The only place I'd really be interested in using the multispectral would be over that denuded veg island. And there, it would show us where the vegetation is, but fortunately it's either bare sand or lush green vegetation. So it's kind of easy to pick that apart, but.
Do we have any other questions for Zach? Are there any questions online? I don't see anything in the chat. No? All right, well, with that, let's thank Zach one more time.